In my presentation title, N stands for nitrogen. This is a follow-up presentation. At our last presentation, we introduced a sustainable ammonia economy. We propose to utilize ammonia as a transportation fuel and to prepare renewable ammonia for energy storage. Today, the focus of my presentation is the detection of nitrogen compounds using electrochemical sensors. Electrochemical sensors are basically an electrochemical cell used for analytical purpose. We use the electrochemical sensors at home to detect gas leakage. One of advanced applications for electrochemical sensors is for neuroscience study. The core component for electrochemical sensors is microelectrode. The microelectrode means the electrode has a diameter of human hair or smaller. Today, microelectrode becomes smaller and smaller, but the smaller the electrode, the more likely the electrode gets folded. My strategy is to develop a nanoporous microelectrode. The nanoporous microelectrode has a high folding tolerance. Nitrogen has 5 major forms: ammonia, nitrogen gas, nitrogen oxide, nitrite, and nitrate. We use the electrochemical reaction in the table for sensor applications. The microelectrode sensor principle based on current concentration relationship. Normally, we apply potential to the electrode and measure the current responses. There are 2 major responses. For the preparation of microelectrode, we normally use a template approach. The first step is the growth of nanoporous material into the template. After removing template, we get a nanoporous layer. The crystal we use is a liquid crystal. There are a lot new for us, and the liquid crystal is a mixture of surfactant and water. They can form a special structure. We use the special structure as the template. We first dissolve the metal salt into the template. After removing the surfactant tablet, we get a nanoporous metal layer. First, we produce the nanoporous platinum microelectrode using the liquid crystal template approach. On the high-resolution electron microscope, we can see nanoporous structure. We use the same approach to prepare nanoporous palladium electrode. The palladium deposited layer has a leaf-like appearance, but the leaves are not solid. They have a nanostructure. We further developed this approach for the preparation of the microelectrodes of platinum-based alloys. We can say that electrode has excellent nanostructure, but sometimes liquid crystal template is not available. We developed a new approach, electrochemical alloy and de-alloy. We first introduced the second metal component to alloy with the electrode substrate, and then we get rid of the second atoms. Here is an example. We prepared the Nanoporous Gold microelectrode. The electrode has a cookie-like appearance. We can say the nanoporous structure. We further studied the influence of driving forces on the electrode microstructure. We apply potential, use a potential stat to modulate the potential and then measure the difference. We studied the influence of responses of microelectrode to nitrite solution. We can say nanostructuring microelectrode produces significantly different. The sensitivity is increased, but sometimes platinum or palladium not available. We produce a very simple microelectrode, the Biochar microelectrode. We simply sealing Biochar fiber into glass. We can say the Biochar is well sealed into glass. The Biochar microelectrode shows good responses to nitrite. Increase the nitrite concentration, clearly increase the radial current. I would like to use these slides as my conclusion. My objective is to develop a nanostructured microelectrode of all of transition metals and to develop a remote nitrogen sensing technology. Thank you for your attention.